for an opportunity. This is SSR M. Rafishek from IEEE Karachi section. I would like to thank Mr. Samir Kazi for his valuable presence for Student Activities Committee for this today's webinar. Thank you so much, sir, and we are humble to have you. Please
You are
proceed.
most welcome.
Thank you very much, Mr. Rafi. Mr. Samir Kazi has received the bachelor's degree from the National University of Sciences and Technology in Pakistan in 2001, and he received his master's and PhD degrees from the University of New South Wales, Australia in 2004 and 2009, respectively. He is currently working as an associate professor and the head of the Electrical Engineering Department at College of Engineering, Karachi Institute of Economics and Technology in Pakistan. Previously, he has worked as an assistant professor with the Department of Electronics and Power Engineering at NUST PNEC, Pakistan, and an assistant professor and the head of the Electrical Engineering Department at DHA Safa University in Pakistan. His research interests are network traffic matrix estimation, compressed sensing, UAV-based video surveillance applications, and the Internet of Things, IoT. Thank you very much, sir, for joining us today. Before we begin, all our participants are requested to keep their mics and videos turned off during the entire session. We will have a question and answer session at the end, in which you can raise your hand and the host will give you the opportunity to ask your questions. You can also send any questions or messages to the host through the chat with your name and affiliation at the end. Now, without further ado, we'll hand over the control to our most esteemed speaker, Dr. Samir Kazi.
Okay, thank you very much, host. I hope all of you can hear me loud and clear.
Yes, sir, we can hear you.
Okay, Bismillahirrahmanirrahim. First of all, I would like to thank IEEE SAC team, Section Activities Chair, IEEE KIET student branch, and all the team associated with the IEEE KIET student branch to give me this chance to speak on this topic, which is very relevant, I think, to our students, because slowly as technology is progressing, we are moving towards the Internet of Autonomous Vehicles. But before I start, since this talk is being held by the platform of IEEE, I would just like to give you my brief introduction regarding my activities with the IEEE. So basically, I've been a student member of IEEE when I was still a PhD candidate at the University of New South Wales in Australia. That was way back in 2006. And when I completed my PhD and I joined NUST PNEC as an assistant professor, I was basically assigned the duties of the student branch counselor. So I performed my duties as a student branch counselor of the IEEE PNEC NUST student branch from around 2009 up till 2014. And during that time, we also hosted an international IEEE conference by the name of IC4. And I also perform my duties as the technical area chair of one of the technical tracks, as well as the main publication chair of that conference. And during my tenure there, the student branch also participated in various activities and also hosted various events and competitions. After that, I was head of the electrical engineering department at DHA Safa University, which is a new university, as you would be knowing. So the IEEE student branch didn't exist there. And during my tenure there, we activated the IEEE student branch of Safa, student branch of Safa University. And that was in 2015, I guess. And it was started from a scratch. And in the first branch counselor over there by the name of Bilal Mehman. Now he is Dr. Bilal Mehman. He has recently completed his PhD from China. He started the branch from a scratch, and it performed quite well during the first year. I switched to PAF-KIET somewhere in 2016. And along with my duties as a HOD electrical engineering, I was again assigned the duties as the IEEE student branch counselor here. And Alhamdulillah, during my tenure here, we have hosted 2 international intellect conferences here. The first one was in 2017 November, and the second was in 2019 November. And inshallah, the third conference will be due to be held in next year, 2022. And Alhamdulillah, I am also very happy that the IEEE KIET student branch has performed exceptionally well, even during the times of COVID. And it was very heartening for me to note that in the 2020, the second best branch in the IEEE Karachi section. So keep it up, team. And without further delay, I would start with the topic. And the topic I have tried to create is as interesting as possible for you. The topic is, why is Internet of Autonomous Vehicles not as plug and play as we think? Lessons to be learned from the present Internet and future directions. So let me flash the presentation. Let me get a pointer. Okay. So I hope this is all visible to everyone. Can everyone see this?
Yes, sir. Yes, sir, it's visible.
Okay, so let's start. So basically, you must be knowing about the internet. Obviously, you have been using it since you were kids, and now things have progressing forward. And now you hear about new terms like Internet of Things and other stuff like that. And along with this, the new buzzwords are now Internet of Cars, Internet of Vehicles. So this topic is going to be related to that. And the basic aspect that we are going to discuss is, what are the technical difficulties in the implementation of an Internet of Autonomous Vehicles. So most of us think that we have seen so many technology wonders, the smartphone and other things, the smart camera applications, artificial intelligence, and other leaps in data sciences. So maybe the Internet of Cars is also just around the corner, and it won't be long before we would be able to sit in a car which will be driving autonomously, and we will just sit back and relax. So we are just going to discuss some of the technological challenges, and we are also going to draw some analogies from the legacy internet, in which we don't have cars but data packets that we are routing over the network. And we are going to draw some similarities amongst the two, and how the legacy internet researchers solve those issues, and probably we'll be needing solutions of the same sort to have the internet of autonomous vehicles. So let's start. Okay, so the ideas and feelings that come to mind is, if we would be having autonomous vehicles, or in other simple words, self-driving cars, it would free the driver from the stress of driving, traffic jams. The car would be able to find the least congested path based on the accurate real-time traffic information. And the cars, they would be able to avoid the accidents, as cars don't feel tired as human drivers do. They won't be making driving errors as frequently, or maybe not at all. Carpooling would be a possible option. We could be having better planned traffic management, and fewer incidents of road rage and accidents on the road. So these are the ideas that and feelings that come to our mind. And we also see some success stories published every now and then on the internet, and one of these is flashed before you. So maybe this is a autonomous vehicle delivering pizzas to customers. So the pictures are showing all. So you have this autonomous van parked outside the pizza parlor, and the guy receives an order via the internet, and and he loads the pizza into the autonomous vehicle, and the destination coordinates or the GPS, and the vehicle is totally autonomous. There's no driver in it, and it delivers the pizza to the customer, and the customer can take out the pizza after making the payment electronically and authenticating herself. So we see these sort of situations where it seems that already implementations are already underway for autonomous vehicles, and very soon there will be internet of autonomous vehicles. So now I think my internet connection is temporarily a little bit weak. So can you hear me now? Am I audible to all?
Yes, sir, you are audible.
Okay. So let's proceed. So these basically give us a false sense of uh, euphoria that maybe the internet of vehicles is just around the corner, but that is not so. Because, for example, in this pilot implementation, maybe this van is only delivering the pizza in the vicinity of the pizza parlor. So maybe it was covering 2 or 3 blocks. So this is just a very prototype implementation, and probably it is implemented in the COVID times. You can see the guy wearing a mask, so there's not much traffic on the roads. Now what happens is that if you try to make this autonomous vehicle go on a highway, things get very complicated. And that is, although these autonomous vehicles are they are basically installed with high quality cameras and radars and lidars to be able to navigate their way in the traffic safely. But what happens is, if you send the same vehicle on a highway, so you'll be having situations like these. So if you look at the first three pictures here, uh, first one says this is these are clippings from newspapers, and the first one is basically an accident of a Tesla auto vehicle, autonomous car, and the heading says the crash driver was playing video games. So now, as the researchers are implementing these autonomous vehicles, they also have to think of the other more challenging situations in which these cars are supposed to go on highways, and they are also they normally make a driver sit in the car who can take the control of the car if the car is making a false decision and is about to crash. So the human driver is supposed to take the control in that situation, but unfortunately he was playing a video game and the car collided with this barrier and it shattered. Now what happens in a highway situation is you have a lot of challenging image processing to be done, because there are so many cars on the roads that the image processing algorithm becomes very computationally intensive. So what that pizza delivery van could do in an area of 2 or 3 blocks, the computational requirement for a car going on a highway at high speeds, it gets many orders higher. And even if it is equipped with high-end lidars and radars and high-end cameras, there are situations where it makes a false decision. For example, it might have fused this concrete barrier, which is also white in color, probably with the sky, and it didn't see it as an obstacle. So it is still going to be some time when we can perfect all of these algorithms and we will have truly autonomous cars. The second heading is similarly about a Google car which hits a bus. And similarly, the image processing algorithm makes a blunder and the car hits a bus. And this third one is a very recent happening just last month, where a Toyota prototype autonomous van, it collides with a Paralympic athlete. So while these cars still collided with other vehicles or other obstructions on the road, this one it hit a human being. So that is very alarming. That means that the image processing algorithm failed to detect that athlete as a human, and maybe it failed to detect it at all and it hit the athlete. So it is still it will still be some time where we can perfect these autonomous driving cars that they can be driving without any human intervention. So let's come to the topic. So we are now not talking about one autonomous car, we are talking about an internet of autonomous cars. And when we talk about an internet, it is a huge scale network where we are not talking about one car or two cars. So you can just imagine about thousands of cars, hundreds of thousands of cars, which are to be routed on the network, and they are making autonomous driving decisions just like the legacy internet. And instead of packets being routed to from one point to the other, you would be having cars. So this animation is basically showing you a network, and what typically are the elements of a legacy internet network is that we have hosts. Hosts are computer users just like you and me, and they are generating traffic, or they are not generating traffic, they are taking traffic as a sink from the network servers. So you might be downloading some YouTube videos and other web pages. So you are not generating traffic, but you are accessing some traffic from the network. So either way, you have these packets, these red, blue, and green squares are data packets which are being routed, and the circular objects are called routers. The routers are addressing devices on the network. They basically look at the destination IP address of the packet, and they make a forwarding decision. For example, this node A would decide whether the red packet should go on this link or this link or this link, so that it can reach its destination fastest using the least cost path or the shortest path. So similarly will be the case when we will be having an autonomous internet of autonomous vehicles. So instead of these packets, we would be having cars, and instead of these routers, we may be having smart traffic signals or smart intersections that would be guiding the cars as to where they should be going to avoid congestion hotspots and other stuff. So the next slide is going to show you a situation. This is a situation where we see that the internet of cars is somewhat similar to an internet of computers as we have today. In the next slide, I'm going to show you a different scenario in which we'll see some dissimilarities, why we can't treat the cars exactly as data packets. So the next slide shows a situation where under situation of normal traffic, we have these users and they are downloading files, maybe having voice telephony, YouTube videos. And when congestion happens, what happens is that the routers are not able to work fast enough to do the lookups for these packets, send them on next stops. And what happens is that they have a temporary storage place, memory buffer. And when they are not able to do the lookup for the packets fast enough, they begin to store them in this memory. And if the traffic is still fast enough, they do something which is called dropping the packets. Now, what happens if data packets are dropped? The destination side may inform the source side that a particular packet didn't reach us, and it will ask it to retransmit. And that is only true for non-real-time traffic. For example, if you're downloading a file, you can ask the source to resend the packets. But if you are having a real-time application, such as you are watching a cricket match, so what happens is that what happens in that scenario is that it will not ask you to retransmit the packet. It will try to mask the packet loss using some intelligent interpolation techniques. So now we can see that this situation is not very similar to an internet of data packets. Why? Because when congestion happens, you can drop the packets and you may ask the packets to be retransmitted. This cannot be possible with cars. If you have a congestion situation, you simply cannot get rid of this car. It is there to stay on your network. So dealing with congestion on an IAV will not be as simple as on a data network, because you can't get rid of cars as easily as a data network. So you can store the packets, because packets are simply voltages and currents traveling on a wire in the form of ones and zeros. You can store them. If your storage capacity runs out, the packets are dropped. You may ask for retransmission of the dropped packets, but certainly that is not true for cars. So there are some similarities, but there are other dissimilarities too. So let us make us aware of some terminologies before we progress any further. So you might already be knowing about Internet of Things. So basically, Internet of Things are basically devices which are connected to the internet, and they can actively transmit data amongst each others. Obviously, they are meant to benefit the humans, but you give them some particular autonomy that they can easily interface with the physical situations. For example, you must have heard of Alexa, which can use voice commands, and it can do a whole lot of things for you, and other voice activated stuff. You have these smartphones, which are also IoT devices. So they can, of course, with the human permissions, they are given some autonomy, and they can exchange data. And not only the Internet of Things is being used uh, by normal users in the form of smartphones and this, but there are newer applications coming in smart agriculture. So in smart agriculture, you can place the sensors in the field, and they will be reporting when you need to be watering your fields for the irrigation and other things. So the applications of Internet of Things are tremendous. So similar terminology is being used for Internet of Cars, Internet of Vehicles, and Internet of Cars is basically it is uh, it is normally described using these acronyms: IOC, IOV. Internet of Autonomous Cars, IAV, which is also the topic of today. Connected autonomous vehicles, we are also going to cover this. Connected autonomous vehicles is basically autonomous vehicles which can make autonomous driving decisions, as well as they are connected to the other vehicles. Now, why would the vehicles need to be connected to other vehicles? We'll just see it in a while. And that one is acronymized as ICAVs. And there is also some basically categorization of autonomous cars. So these start with level 0, which are completely normal cars which have no intelligence built into them for autonomous driving, to level 1, 2. So you must be knowing about some cars which can have parking assistance. So you just press a button and the car can park itself. Remaining driving is done by the human, but the car can park itself. You must be knowing about cars which can do lane detection, or it can have cruise control, or it can stop automatically if it sees some obstruction or some pedestrian on the road. So it will apply the brakes automatically. So all of these autonomous cars are still in the range of 0, 1, 2. And we are looking at this number. This is a magic number in which the car will be a level 5 autonomous car, and it will be able to drive completely on its own without any human intervention. So these are some examples. There's Tesla Autopilot and Cadillac Cruise Systems. They also qualify as a level 2 car. So these are called semi-autonomous cars, because a human is always sitting behind the wheel, and he is supposed to take over when the car is making a mistake. So this is the definition of the levels of autonomous cars. So we are still somewhere here. We are still somewhere here in which there is driver assistance required, or there's partial automation, and we are looking to be here when we will be needing no human to take over the control of the car. That means that the autonomous driving decisions of the car will be completely foolproof, and it will be not prone to any driving errors, as we saw on the earlier slide. And these autonomous driving decisions are made through a load of sensors which are installed in the cars. Some of them are cameras, radars, lidars, and of course all of these sensors collect some data about the physical surroundings, and the car is still not able to to relate that with the physical surroundings, it goes into an artificial intelligence engine, and that basically gives the decision to the car that what is it exactly, what is it seeing, and what decision it should be making regarding its autonomous driving. Let's move forward. So the topics that will be discussed in today's lecture will be the architecture of the IAV and challenges. So this will be the physical architecture. What are the components forming the IAV? Then the challenges of information propagation models over the IAV, challenges of the navigation models over the IAV, challenges of traffic grooming models over the IAV, and there are some peer-to-peer relay and value-added services which will eventually be run over IAVs, and finally cyber threats of which can disrupt the performance of an IAV. So let's come to the first slide in which we discuss the architecture. So this is the architecture that we suppose would be there when the IAV comes into being. So we can see some cars, and this wireless signals over the cars show that these are connected autonomous vehicles. So they can talk to each other, and they can also talk to the roadside equipment, and the roadside equipment can talk to the infrastructure equipment. So basically we have a central infrastructure, and the central infrastructure probably houses the centralized traffic controller. So this centralized traffic controller would probably be setting the state of the traffic signals. So whenever you are going about in your car and you come to a traffic signal, so you see that the traffic signal has a certain amount of green time offered to different traffic flows. And normally what you must have realized is that if you are going on a very, very busy highway like Shari Faisal in Karachi, so the green time is for more duration than the green times for the intersecting traffic, because obviously the more volume of traffic is going on Shari Faisal. So all of these traffic timing or signal timing is currently based on the statistical traffic models which are being observed by the traffic policemen. But when we would be having the IAV, so these cars will be passing their info to the roadside equipment. So this would be some roadside street equipment, and this roadside street equipment will probably be sending this info to the centralized traffic controller, which will be able to adjust the timing plans of these traffic signals. And there are some acronyms here which will be on presented on the second slide. So this R basically refers to roadside equipment, I refers to the infrastructure equipment, and V refers to the vehicular vehicles. So V2V communication is the communication between the vehicles. V2R is the communication between the vehicle and the roadside equipment, and so forth. And there, of course, can also be some cloud-based services. This information could be fed to the cloud, and some third-party people could be making some good inferences on them, and they may be sending some more value-added services. So these are the acronyms that we just discussed. So physical layer communications have to be wireless in an IAV, of course. You cannot have a tethered network. So these are the various nodes that will be communicating wirelessly: vehicle to vehicle, vehicle to infrastructure, vehicle to roadside equipment, and so forth. So what are the physical layer technologies as buzzwords? So we have some IEEE standards. One is called the dedicated short range communications standard, which is called DSRC, which is based on the IEEE 802.11p standard. So you must have already been using laptops, and you already know that 802.11 A, B, G, N are standards which are used for mobile equipment such as laptops. But obviously cars are not similar to laptops. They are traveling at higher velocities, and also they are also prone to weather conditions. You will always use a laptop inside the safety of your home, but the cars are meant to be traveling on the roads, and there might be thunderstorms just like nowadays. So there might be bad weather in which still you need to communicate effectively, because if a car is not able to communicate its information effectively to the roadside equipment, for example, or it cannot get the information from the roadside equipment, so there are chances of accidents. Similarly, the other standard is called WAVE, wireless access and vehicular environments, which is again an IEEE standard 1609.x. So these standards are already in place, and whatever cars you are seeing nowadays being tested on test rigs, they are already using these transceivers based on these wireless technologies. And in 2016, the US Department of Transport has already designated a band specifically for the IAVs, and that band works in the 5.9 gigahertz range. So there's a lot of research interest in Internet of Vehicles. Now the challenge is high data rates due to high number of sensors. So if you take an autonomous car, it has got plenty of sensors related to the braking system, related to the velocity, related to the lane information, related to acceleration and other stuff. So you have to communicate all of this data reliably between the vehicles and from the vehicles to the roadside equipment. For example, if a car is coming too fast and the traffic signal is about to turn red, so it might run an AI and algorithm, and it might say, okay, this autonomous vehicle will not be able to stop in time, so it might give it a green corridor for a little more while. So these are the challenges that are posed. So let's see some real case scenarios why a vehicle to vehicle and a vehicle to roadside communication would be required in an IAV to coordinate amongst each other. So this example is basically showing you a smart intersection. That's why it's labeled with a wireless signal. And we have these smart cars, these red cars. Again, they are labeled with these wireless signals to show that these are part of the IAV, and they are also connected vehicles connected to each other. They can also communicate with the roadside equipment such as the traffic signal, and they might be in the presence of conventional unconnected cars shown in gray here. So the vehicle to infrastructure control would be for these cars. They probably are going towards the same destination, so they decide to move in a platoon. Platoon is basically just a coordinated movement of the cars, where there's a one leader car and some cars which are following it, keeping minimum safe distance. So this V2I control would basically be talking to the platoon leader, and the platoon leader might be communicating its decision to its followers over the V2V communication. So for example, okay, I'm going to turn red, you must slow down. So he must communicate this to the follower vehicles that I'm going to decelerate, so that these vehicles also activate their deceleration. Otherwise, there might be a collision. Almost there is a chance that there will be a collision. So this car has to inform about its own autonomous driving decisions to its follower vehicles, which are following this car due to the fact that they are going for the same destination. And it's good that they are not stuck in a traffic jam and they are moving like a platoon. Similarly, the V2V communication, it might be used for lane detection. For example, if the lead vehicle decides that I have to change my lane in order to speed up, it also has to tell the same to its follower cars, so they can also change their lanes in time. And of course, all the braking, acceleration decisions have to be communicated timely to the follower cars so that they can maintain the safe interdistance. Another situation will be coming later. So for the roadside to roadside and roadside to infrastructure communications, you normally use technologies which are not those ones like wave and DSRC. They are basically more high powered wireless networks. So they might be wireless mesh networks or cellular technologies. So when the cars need to communicate with the infrastructure equipment, or the roadside equipment needs to communicate with another roadside equipment, so you normally know that a traffic intersection might be several kilometers away from another traffic intersection. So DSRC and wave won't work under those scenarios. So you have to take the help of cellular networks. So you can have these 2G, 3G, 4G networks, which help in facilitating large distance communication, such as between one roadside equipment to another, or one roadside equipment with some infrastructure equipment. And these communications will also be helping to make centralized traffic control decisions. This is another example where a smart intersection may coordinate. So these platoon of cars is moving towards a smart intersection, and the smart intersection, since this is a dominant traffic flow here, so it might turn the right red for the cross traffic and allow this platoon to move without any interruption. And when it is about to approach the second intersection here on the right, so the same would be done by the second intersection. So it will give a green corridor to the dominant traffic flows. So again, this is not possible without the roadside to roadside communication and roadside to infrastructure communication. So let's move forward. So now we are closing on to our target discussion, which is why Internet of Autonomous Vehicles are not as plug and play lessons to be learned from the legacy Internet. So we are going to see some similarities and dissimilarities from the legacy Internet, which can help IAVs to solve the problems that may crop up, just like in the legacy Internet, the legacy data Internet. So if we consider that Internet users are selfishly trying to optimize their performance by getting the maximum of network resources, then the same principle also applies to the IAV. So what we mean by this sentence here is, when we are using the Internet, we are basically trying to be selfish. If you are downloading a movie, you want that movie to be downloaded as soon as possible. Do you care about your peers? Do you care, oh okay, I don't mind, maybe this movie can download over a time of 5 days so other users can have good quality of service? No, everyone wants his own quality of service to improve. He's going to be going for more and more expensive higher bandwidth connections. So you are basically making selfish decisions. You want to optimize your quality of service, and this may be coming at the expense of the quality of service of others. Similar will be the situation with IAVs, where everyone would want to, where every autonomous vehicle would be making selfish decisions to get to its destination on time, avoid traffic hotspots and other things. Now, the users are making a selfish decision, but if we look at from the network view, the network basically is designed in such a way that it wants to give an acceptable quality of service to everyone. So the legacy Internet, when it was designed with the purpose of best effort service, not the best service, but the best effort service. What I mean by the best effort service is, it basically ensures that every person on the Internet will get an acceptable level of quality, and there should be no selfish users which will be demanding more and more network resources at the expense of others. So we are going to see this in detail. It will become clear. Similarly, selfish routers, or in this case, the selfish intersections, may selectively optimize their own performance. For example, What we also see in the internet today is there are some premium customers of your ISP, and your ISP might be giving them preferential service. So what happens is that the packet goes to the router, and the router sees, oh, is this the premium customer or is this the regular customer? So if it is the premium customer, it might do the lookup quickly and send it off to its destination. And if it is a regular customer, you may end up in that buffer that was shown in the last slide. So the routers basically have some routing algorithm in which they exchange some state between each other. This is through a gossiping algorithm. So I'm just presenting this slide because the discussion that will follow later will be related to this. So the routers, they basically gossip with each other, just like the women gossip with each other, and they tell us, oh, I'm connected to this guy and this guy, and this router will tell, oh, I'm connected to this guy and this guy and this guy. And in this way, they are going to get a view of the network, and they are going to populate their routing table. So when a packet comes, for example, to this router, it will look up its destination address, and it is going to send it off towards its destination using the least cost path or the shortest path. So similar will be the situation with the IAVs. Now, the information propagation models, what are the challenges even in the legacy internet? So just as I told you that the information exchange using a gossip algorithm. So the neighboring nodes, they gossip with each other, and they tell their view of the network to each other. And in this way, the topology of the network is formulated. So if you do an incorrect information exchange or display some selfish behavior, then this topology information will be propagated. It will be propagating false information, and the whole view of the network may be corrupted. So we are going to see this. I'm going to show you an example where incorrect topology information can disrupt the whole network. And basically, you might not be exchanging the topology information in an IAV, since the network topology is already known. And this is a different matter, that in a legacy internet, the topology of one network is known, but the topology of the other network, for example, if you are routing your packet through an ISP in the US, so that US ISP will not reveal its topology. It will only reveal a little bit information that may be helpful in routing. So what do you basically exchange in an IAV? The topology is already known. So you would be exchanging information about current traveling delays, origin destination of the travelers, which will be helping in making the traffic plan. But if you selfishly keep some information or propagate false information, then the whole view of the network is disrupted. I will show you a case study in the next slide. So you can have centralized policies and distributed policies. So what to do with the information that is propagated? So the information is propagated in a distributed manner, as we saw here, that all of the guys, they are using their local information and they are distributing this knowledge to the whole network. So a centralized view could be seen. So what you could do is you could send this centralized view to a central entities, such as a centralized server. But the problem with the central entity will be it might become too overloaded, too slow. So normally what we do is we go for distributed decisions. So what these routers will do is they will exchange this information, and they will make this routing algorithm completely in a decentralized or in a distributed manner. So they are not going to rely on some central server in order to make these tables. So this will all proceed in a distributed manner. And the reason being, if you have a central entity calling the shots, then you can basically have a potential bottleneck. What if this thing is hacked? What if this thing goes down? Then the whole network will cease to function. So normally information exchanges in very, very large networks are in a distributed manner, and the policies are also made in a distributed manner. You can have information proceeding in a proactive manner or in a reactive manner. What happens in a proactive manner is the information is basically propagating every once in a while, because the view of the network may change. For example, in a data network, a link might go down, a submarine link might go down. So information is proactively exchanged every 5 minutes, with something known as a handshake protocol. So, and at other times you basically request the information yourself when it is needed. So example, when you would be needing some navigation decisions to go to a particular place, so you might ask for that information in a reactive manner. Now I'm going to show you how the information propagation going in a distributed manner can completely disrupt the network, by showing you an example of a real internet test case that happened in 2008. And the case was that in 2008, around 2008, there were some malicious videos posted on the YouTube, which were against the Muslim and the Islam and the Prophet Muhammad sallallahu alaihi wasallam. So what Pakistan wanted was that it wanted to shield its customers from those malicious videos, because Pakistan cannot obviously take down YouTube. The YouTube servers are in a different country, and which is governed by different laws. So let's see how basically Pakistan, the distributed information travels. So this is an ISP-C, which is connected to the YouTube servers with a cost of 8. So it is going to gossip this to its neighbor ISP-B, and it will say that I can reach the YouTube servers with a cost of 8, and the YouTube servers are internal to my network. That means the servers are inside this ISP in one of its data centers. It will propagate this to B, and B will say, oh, I can get to YouTube through C with a cost of 18. It will propagate this to its neighbor A, and finally the neighbor A will judge that I can reach the YouTube through going networks ISPs B and C with a total cost of 10 plus 11 plus 8 is 29. So it's going to inform this to the gateway router of the Pakistan, and the Pakistan router will have this entry installed that I can go to YouTube through a cost of 29, but I will have to go through ISPs A and B and C. So this route is installed in the Pakistani gateway router. Now, in order to deceive its internal customers into not being able to access YouTube, because it cannot do about the other world, since the YouTube is not under its control. The people in the other countries are not under the control of Pakistan. So it wanted at least to shield its internal users from those blasphemous videos. So what it did was, it made a fake YouTube entry in its router, and it kept the cost very low. The cost was kept as 0.00002. So whenever a request for YouTube would come to the gateway router, oh, the gateway router will say, I can get to YouTube with a cost of 29 going through A, B, and C. And oh, here's a new path. And this is way, way less than 29. It's just 0.0002. So it will not prefer that original entry of cost 29. It will prefer the low cost path. It will go to the fake YouTube site, which is actually a black hole, and the request will be lost here, and it won't be able to pull the actual blasphemous video. Now, what happens was that since this protocol proceeds in a distributed manner, what it did was it also advertised this path accidentally to the other world. So what happened was it advertised this path to ISP-A, which in turn advertised this path to ISP-B, which in turn advertised this path to ISP-C. And what happened now was they said, oh, there's a very, very low cost path through Pakistan. So all of them also did the same. They ditched their original path because they have now a lower cost path. So they said, oh, we should go to YouTube through Pakistan. And when they went through Pakistan, the traffic ended up in a black hole. And actually, the whole YouTube traffic was disrupted for the whole world, not just for Pakistan. So similar could happen in an IAV. If any selfish information is propagated, even accidentally, the whole IAV network could go down. So this is a practical scenario where we can have selfish information propagation. So in the normal scenario, we want a central entity to be making all the traffic routing decisions, but sometimes even the central entity may become helpless. So for example, there's a busy highway and these red cars are connected cars, these green cars are also connected cars, but the difference in color shows that these red connected cars are stuck in a traffic jam. Now this might be due to an accident on the highway, so there might be a truck overturned on the highway and there's this congestion happening, and no matter now what the central entity does, even if it gives the green time for infinite amount of time to the dominant flow, the dominant flow cannot make any progress due to this. So now there's something in the regular internet which is called peer-to-peer measurements. So instead of asking the central entity for its view of the network, what the guys do, one IAV might query another IAV about its view of the traffic, and these red cars will communicate, oh, there's a big traffic jam here, do not be coming on this side. So these green cars will then query other cars and they will finally find an alternate path. So the alternate path, which is called a detour, is found without the network help. So this is a selfish decision on the part of the users without informing the central entity, and it will basically be defeating its purpose of keeping the network in a good condition, because maybe this path may eventually get congested too, and that won't be due to the decision called by the central entity. So let's move forward. There are again challenges to the navigational models. So what challenges can we have here? So navigational model is basically you want to go from point A to B and you want to ask the network what is the best possible paths, similar to what you do today. You go to the Google Maps and the Google map will basically give you the best possible path and possibly one or two other alternative paths too with the potential projected driving times. So you basically have the challenges again here, that if you have a centralized system or a distributed system, so what challenges could they have? If you are querying a single guy about the traffic situations, you can have again scalability issues, single point of failure, just like was the case with the information exchange models. Traffic conditions on the road may vary quickly. By the time the central entity has run its algorithm, the situation has already changed. So, and there could be some selfish peers not sharing their measurements truthfully. So these are all the problems that could be plaguing the centralized models. So you may have distributed models, and again they could be suffering from selfish behavior. So for example, there's one very well known situation called hot potato routing, even in the legacy internet. So we can see how hot potato routing disrupts the behavior in the next slide. So this autonomous cars, connected autonomous car, comes to a routing autonomous routing domain. For example, it wants to travel to I don't know, maybe Clifton or Defense, and it comes and the shortest path maybe goes through Nazimabad. So it comes into the Nazimabad autonomous routing domain, and it requests for a shortest path going through Nazimabad, connecting to the next autonomous routing domain, eventually leading to the destination using the shortest path. But when this Nazimabad autonomous routing controller looks at the destination or sees, oh, the destination is Clifton, so this guy is going to be congesting my roads in order to go to Clifton, which is not even inside of me. So it will say, let's kick this out as fast as possible. So that is the concept of hot potato routing. So it will not be, now this is a selfish decision on the part of the network, not of the user. So this network says, why should I be congesting my roads for this guy who doesn't even want to end up in somewhere inside me? It wants to go to Clifton. So it will give it some false selfish information. Oh, the shortest path is not through me, my roads are congested at the moment. So what you can do is you can go through my neighbor, probably he has a good path, so he is going to kick him out. And eventually what will happen is, due to the selfish distributed routing domains, making selfish decisions, this guy will eventually be going from an optimal path to a less than optimal path. So there can be selfishness on both the part of the users as well as on the part of the network. So we can see one classic example in the next one, in which when the user knows that the network will also be making selfish decision, and the network also knows that the user is also after selfish or preferential service. So there might be many third party services or peer-to-peer services in which neither the selfish user relies on the selfish network, nor the selfish network is able to help the selfish user. So they will be relying on a third neutral party, which will be giving them the best view of the network and how they can navigate using the optimal path. And for example, this third party can give them the optimal path. Even things then are not settled. Why? Because there is again a potential of network disruption. And I can give you a classic example. There is something which is called wardrobe equilibrium. So we are going to take a test case, and we can see that why even this technique may not work in order to get the client the optimal navigation model. So this is a view of the network in the shape of a graph, and we can have these circles representing routers or intersections, and we have these roads being shown as edges connecting these nodes, and there's some number written below the edge, and that number basically shows you the cost of using that road. So for example, if the number is 100 plus n, so n represents the number of cars on this road. So currently it is 3 cars. That means the cost of this road is 103, and we are going after the least cost path in order to optimize. So this cost could be maybe traveling delays, and obviously lower traveling delays are better. So the lower the cost, the better is the path. The cost here is 20n, so it is 20 times n. There are currently 3 cars, so the cost of using this road would be 60. And if a guy wants to go from A to B, he has a choice of 3 paths. The first one is A to C to B. The second one is A to D to B. And there's a third one in which he can go from A to C to D to B. So initially, let's assume we have some unconnected cars shown as beige, and we have red cars and blue cars. Both of them are connected cars, and red is subscribing to service A, and the blue cars are drivers which are subscribing to a third party service B. And whenever they want to travel from a point A to B, they refer or they ask their respective service, and that tells them the optimal path. So in this case, all of the cars are meant to go from A to B through this network. And when the red cars query their service A, it says, oh, the best path for you to go from A to B is via C. So you can just go from A to C to B. So we can see these red connected cars using this path. And similarly, when the subscribers of service B, the blue cars, they query their service, they say, oh, the best path is from A to D to B based on the current traffic measurements that we are getting. So we can see that the blue cars are also going using this path from A to D to B. And then there is some background traffic of unconnected cars. So if we do the math, so the path taken by the red connected cars has a total cost of 20 into 3, 20 into 3 for this link, and 100 plus 3 for the second link. So this has a total cost of 163. And similarly, the path preferred by the service B for the blue subscribers, blue connected cars, that also has the same cost, which is 163. 100 plus 3 plus 20 times 3, again coming to 163. But then when the measurements go to both the service A and B, it sees, oh, there's a better path. What if our subscribers go from A to C to D to B? How will the cost be lower then? So the cost is definitely lowered. The cost becomes 20 times 360 plus 21 plus plus another 20 times 3 is 60. So you have a 60 plus 21 is 81, and 81 and another 60 is 141. So now the service B is going to tell its subscribers, the blue connected cars, and the service A is going to tell its subscribers, the red service cars, oh, you can have a better path with a lower cost, 141. Initially, the path that we propose to you, it has a higher cost, and we have a lower cost path available. So now what it will do is, it will ask its users respectively to switch to the new path, which is A, C, D, B. Now see what happens now. So this is the initial situation. And now what if the red connected cars and the blue connected cars switch to the new path A, C, D, B? What happens now? Now note that we have not added any new cars or removed any cars from this example. So this example had 13 cars and all, and this example has the same 13 cars, but they are redistributed. So this is 4 plus 3, 7, 7 plus 4 is 11, and 12 and 13. So we are not doing any suspicious behavior here. These are the same cars, but they are now redistributed because both the red cars and the blue cars are now redistributed on the newer path A, C, D, B, which was suggested to them by their third-party navigation service. And look what interesting situation happens. So they both choose this path. So now the path has a higher cost because both the blue cars and the red cars have switched there. The background traffic is not modified in any way. So there were 2 cars here before, there are 2 still here. There was just 1 here, there's just 1 here. There were 2 here before, so there are again 2 here. So the background traffic is also perfectly the same way as before. And now let's see what is the cost now. So the path cost is now 20 times 4, since there are 4 cars here, plus 20 plus 3, since there are 3 cars here, and another 20 into 4, and the path cost becomes 183. So the path cost jumps from 141 to 183, and that means that obviously both of the services switch to this one, this path. So we did expect that the cost would go up, but now we would be wrongly thinking that now the third party service will say, oh, now go back to your original paths, which was 163, because 163 is now lower than 183, but we are wrong here. So what the wardrobe equilibrium tells us, that if we look at the original paths, the path costs have still increased, and it is not 160 anymore. It has again risen to 181. So you can do the math. 20 into 4 plus 100 plus 1 is 181. So now we can see that such disruptive behavior is very, very hard to contain. Is very hard to contain. So once this selfish behavior goes on a network, it is very, very difficult to contain it. So let's move forward. Now we come to the traffic grooming aspect. The traffic grooming basically relates to how well behaved the traffic is. By a legacy internet network, we basically mean that the traffic sources should be well behaved. That means if anyone is demanding traffic from the network at 5 megabits per second, and there's another guy who says, oh, I don't like 5 megabits per second, I want 1 gigabits per second. So that will be called a misbehaving source, because when it will be causing so much traffic congestion on the network, it will be at the cost of the QoS of the other users. So similarly, we might be having traffic grooming issues in the IAVs. For example, in a particular scenario, Sadr, which is the root hub of the business in Karachi, it might be having a very, very huge traffic demand during the rush hours, because everyone converges to the central business districts of some cities, and it has a much, much higher traffic demand than the other parts of the city, such as the suburbs. So in that situation, it becomes very, very difficult for routers and for example, smart intersections in an IAV. how to do the traffic grooming, because once you have a huge rush of traffic coming to these intersections, then the intersections is not able to cope up. So you want to fix the problem straight at the origin, that so much traffic should not be coming to the central arbitration points, so that it has to be in a problem. So how do we do the traffic grooming? So first of all, let's look at the situation in a regular traffic signal. So whenever you must be going to a regular traffic signal, you see that it basically works in a round robin manner. So what does a round robin manner? You basically get a green time for this part, then you get a green time for this flow, then you get a green time for this flow, and then back it is to the first flow. So this is called a round robin scheduler. And obviously you can have differing amounts of green times for these traffic flows, but goes in a clockwork. But this is very, very inefficient because it is non-adaptive. Why? Because you might have seen situations where you are returning home late from a party at 12 o'clock, and you are basically wasting your time at a red light over here, when you can see that there is no traffic here or here, and the green time is extended to the empty roads, so you get frustrated. So you basically want an adaptive traffic controller which can make real-time decisions. So what happens is, how you can groom the traffic coming at the intersection. So this is a toy example from a computer network, and you can see a router over here. It has 3 input ports, A, B, and C, and 4 output ports, 1, 2, 3, 4. So these packets coming to ports A, B, and C have a situation where the first packet of each wants to go to destination port 1. Now, this situation is called head of line blocking. Why? Because it is fairly obvious to us that at any one point in time, only one of these packets could be routed to the output port 1. So if they are basically in a contention, then you have to resolve the contention. How you can resolve the contention is, the easiest way is, okay, you can give it a turn by turn. Okay, first it's your turn, then it's your turn, then it's your turn. This is called this is a very crude scheme called a take a ticket scheme. But in this way, you can see that the packet from this port A will be routed to output port 1, and after that this packet will be routed to output port 1, and then this packet will be routed to output port 1, and you can see that other packets were not able to make progress in this manner because of the contention. So what happens is, in a real router, you basically go for more optimal schemes, in which you see when a progress cannot be made, you try to reorder the packets so that you are not wanting to serve them in a first in first out manner. So the problem here was, you are basically trying to serve them in a first in first out manner, and it might cause contention in some situations. So what you do is, you basically reorder the packets. So you treat the packet in parallel, and you try to find the perfect matching so that you can create most progress in one go. So this is called packets served out of order. So you can reorder the packets because the packets are stored in the router memory. They are just bits of voltages and currents. But the $1,000,000 question is, can cars be served out of order? Can they? So there are many groups in MIT which are working on the concept of IAVs and constructing smart intersections with smart centralized arbitrator deciding upon the transmission time and path to the network. So they basically have devised something which is called a slot-based intersection arbitration. So for example, if this car is causing a head of line blocking, it is preventing these cars who want to go straight because it cannot have its own way through the network. So what the network will do is, it is going to rearrange these cars using a queue management and traffic scheduling algorithm, So it was going to base the access of this point, this intersection point, through slot based. So it is going to grant them access numbers. For example, this car, which is right at the end, if it was over here, and if this car, which is positioned here, if it was here, then the cars could go without any contention. So it is going to assign these slots to the cars. So it will ask this car to accelerate and move forward, and maybe this car to decelerate, so that when they come at the central point, they can continue their journey probably without waiting for any red light. So this is how a head of blocking problem, which is a very, very common problem in the legacy data internet, can also crop up in an IAV, and it can borrow some concepts from the legacy internet to do the traffic grooming through intelligent queue management and traffic scheduling algorithms. Then there's also an aspect of the traffic where a high amount of traffic flow, for example, to Sadr, it might cause problems in the other parts of the network due to high traffic flows. So this is how the legacy internet deals with the problem. So whenever a new source comes on the network, it allows it to increase its flow of traffic or rate of flow of traffic, first in the manner of an exponential increase, then in the manner of a linear increase. And this is called the congestion and flow control algorithm. TCP basically implements this in the internet. And whenever there is a congestion in the network, for example, you ramped up your traffic volume rate because the network was allowing you, and you went up to this point, and suddenly then there is a congestion in the network. So the network is going to punish you, and it will say you restart from one packet because you were sending so much traffic that it caused some congestion in the network. And while you reduce your volume of traffic injection into the network, it will basically give a chance to the others to increase their traffic flow. So this basically ensures the fairness in the network. Now, this same example cannot be applied one-to-one on an IAV. So what an IAV could does is, there's a particular traffic regulator and shaper used in the legacy internet, in which basically it is called a token bucket regulator, and it adds some tokens into a token bucket. This is implemented as a computer algorithm, of course, and it basically, if there is a very, very large surge of traffic which wants to be injected into the network at this point, it is basically going to reduce that volume of traffic. It basically will make the traffic first accumulate some tokens in this, and then it is going to discharge a particular small subset of this traffic into the network, while the other guys will have to wait. So this is going to regulate the traffic flow into the network at the injection points, so that it doesn't cause any congestion later in the network. So this is another concept from the legacy internet that the IAV could borrow. So I'm about to finish my presentation in a little while. I've exceeded the time limit already. So there's a peer-to-peer aspect, data relaying aspect, value-added services over the IAVs. So as IAVs will become common, apart from the crucial sensor data and the traffic data, for example, traveling delays, congestion data, that will obviously be routed over the IAV for its functioning. There might be non-IEV based services, for example, personal data services. So you might form a peer service with some other cars which use the same commuting routine as you, and you might, for example, you must be knowing about the BitTorrents and other peer-to-peer services in which you can download music and movies from your other peer friends, and similarly return the favor by allowing them to download data from you. So such can also happen over IAVs, but the only difference would be that it will be data exchange between one car participating in the IAV and the other car. So you must be knowing about the 5G and the 6G services. So that can allow very, very high data rates over short distances. So you might be able to use those to transfer huge amounts of data in a little amount of time with cars which are commuting or near you, or they use the same traveling routine as you. You might be having more value added services. For example, you might reveal your traveling plans to third party services, just like you have on the Google, where it is recommending you restaurants near your home, or it is recommending you petrol stations where near the places you are traveling and other things. So you might be having these similar value added services. And of course, the IAVs could be acting as relay nodes for other data networks. For example, a wireless network which is not based on the cellular network. It has limited transmission range. So one IAV could act as a relay for the other one. And this is definitely true for the wave and the DSRC, which have a limited transmission range. So coming to the second last point, challenges of cyber attacks on IAVs. So what are cyber attacks on IAVs? Just like you can have attacks on your computer terminals and a legacy internet, where a guy can pose as you and hack into your network and maybe steal funds from a bank, or maybe it could not steal funds from a bank, but it could pose as you, and maybe it could order things online using your credit cards and other stuff. So similar things could happen on an IAVs, but the consequences could be more disastrous. For example, it might spoof your GPS coordinates and make you think you are in another place than you actually are. And you are thinking that you are going towards your destination, but it is taking maybe to you to a remote location, and maybe your car may be able to perform as an accessory to kidnap you. And you can have other attacks, for example, denial of attack services. So you might be asking for a service, and due to a DOS attack, the service provider cannot entertain your request. You could have more severe circumstances in which you are thinking that your firmware of the car sensors is being updated, or the sensors are being recalibrated, but actually it's a malicious attack, and they are basically giving false information, update information to your sensors, and then your sensors are not able to function properly, and your IAV maybe could be in a collision. And there is something also known as the onboard diagnostics board, which is an interface to all the electronic systems, electronic control systems of your car, and a hacking attack could also be possible. So there's some statistics on the next slide, and it shows 50% of the OBD ports currently are vulnerable to attacks. So in an IAV, this will be very, very crucial to safeguard your autonomous vehicle from any cyber attack or threat, which may be very, very disastrous. In the last one, again, there are some moral issues, and the moral issues are you are loading all of these cars with AI based algorithms and these good fast computing hardwares, and you expect your car to be able to detect pedestrians, other cars, obstacles on the road, take you to your destination in the shortest possible time. Can the cars in an IAV make moral decisions? Okay, by moral decisions, the scientists or the researchers means that, for example, you are going in your IAV, and for example, the brakes of the IAV are not working well enough, and you have to collide with two objects. In one, there's a group of 5 people, and in the other one, there's a group of 10 people. And if you would hit your car with one of them, then there is also a certain damage to the car itself. So will the will the car decide to collide with the group of humans, or it will decide to collide with a third entity and put its own drivers at risk? So these are the sort of things which are still being debated. Would the autonomous driving cars, especially in an IAV situation, they will be able to make moral decisions? So with that, I come to the end of my this presentation, and I hope I didn't spoil your Sunday, and you certainly are more informed about this topic. Okay, thank you all.
Thank you very much, sir. It was a very informative session, and I'm sure that everyone else in this meeting feels the same way. If anyone has any questions, kindly raise your hand so we can unmute you, or type the question in the chat box along with your name and affiliation. Sir, we do have a question in the chat box. It says, since you were talking about artificial intelligence-based algorithms, is it possible to integrate IoT with artificial intelligence?
Yes, that's a very good question. So basically, what I want to tell here is that basically IoT is basically up till now the feeling was that it's just devices, some dumb devices which just have sensors in them, and they're just relaying their information to some other powerful entity over a wireless network, and the artificial intelligent algorithm was working in that powerful computationally in a powerful device, and then it can then decide upon something, and then the information comes back to the IoT network to probably activate an actuator. But the recent research now is now focusing on making the edge devices more intelligent. That means now they want to make the AI algorithm to exist on the device, edge device itself, which may be an IoT device interfaced with some powerful Raspberry Pi computer or some other system on chip. So you will basically be having some AI algorithm which is pre-trained on some powerful device such as a GPU, and the trained results of that algorithm, they are basically put into that edge device, and the IoT will consult its own it will not have to rely on some external entity. It will have an onboard AI inference engine in which it can put its parameters, and probably it can have a decision that it can make right away. So the AI algorithms, for example, in the IAVs, they are also meant to work on board. They are meant to take the decisions on board. So the AI algorithms, the pre-trained AI algorithms are already loaded into their firmware, and the sensor readings go to the neural networks or the convolutional neural networks, which is pre-trained, and the convolutional neural network is going to give it some decision. Okay, the guy that you are seeing in front of your camera, it is a likelihood with 70% that it's a human being, or it might erroneously, like I said, sometimes the AI algorithms are deceived. It might see a pedestrian, but it might tell the car, no, it's not a pedestrian. It's only a 13% chance it's a pedestrian, so you don't mind about him, and the car will unfortunately collide with the pedestrian. So it's basically about the perfection of the AI algorithms, as well as the images acquired via the cameras. For example, the AI algorithm might be very good, but sometimes you have a very sunny day or a very clear sky, and you might have a white truck or a white bus going against a clear very white sky or light blue sky, and the camera basically acquires an image, and due to there's something called overexposure when there's so much light, so the image going into the AI algorithm is actually not good enough. for the AI algorithm to be able to make a good or correct decision based on that. So it's basically multiple factors that are in play here.
Thank you very much, sir. We have one more question. Is cloud a good option in vehicular communication as it can cause delay?
Yes, that's a very good question. And as I was talking about in my talk also, that most of the time you might want to consult uh, the cloud, because a cloud is no more a dumb cloud. It is giving you facilities. It can take your data, process it. It can offer you loads of other stuff as a service. But going to the cloud, definitely it incurs a delay. And sometimes in autonomous driving, you might not be able to have that much liberty up to your disposal. So some services which are not real time intensive, you might be able to query the cloud. For example, you want to go from a place A to B, and you can refer to the cloud based some software that which is the good route to take. But if you are talking about a real time driving decision, so that may be only be between the vehicles and the roadside equipment that is in the vicinity. So you might not want to go to the cloud for that.
Thank you very much, sir. We have just one more question. Sir, in your opinion, what is the scope of this field in future? And what is the impact of this field on manual cars?
Well, that is difficult to say what future directions are going to be, but the scope is that you are definitely seeing Google, Tesla, and many other giants investing in this field. So definitely there's a real interest in this field, and amongst other services that we have been seeing that look like a fairy tale a little while ago, but they are now all a reality. So definitely these fields are going to mature, and just like you are seeing headlines that the electric cars will take over in the next 15 to 20 years. Already government is offering incentive for electric cars, and the fossil fuel cars will become obsolete overnight. And I don't know about you, but while I was growing up, I saw the technology of the magnetic tapes drives, floppy drives, and the VHS, and now they are all obsolete. And most of the audience here, they must have never seen it even in their life. So we can safely say that if these AI-based algorithms are perfected and we can go to level 5 autonomous cars, then definitely this IAV will be a reality in not in the near future, but few decades, I must say. And most of the fields that are related with this IAV, they are already working. They are already working in bits and pieces. For example, how to perfect the object recognition technology. You already know that now the Google search button, it already now has a camera tool also, in which you can take a snap of anything you are seeing with your camera, and the Google is going to search it on just the base of the image. So these technologies are definitely integrating into our lifestyles at a slow pace, and definitely IAV will be the next.
Thank you, sir. We received one more question for you. Is smart vehicle and autonomous vehicles the same?
That's a question that I think I've already answered in my presentation. So basically, there are levels of smartness. I had shown you a slide. Maybe I could go back to it. So basically, the definition is not a you cannot just answer it in black and white, that this is a smart vehicle or this is not. So there are some shades of gray to it. So you might have a vehicle which can do cruise control and lane detection. So you might call it a semi autonomous or a semi smart vehicle. So a completely smart vehicle, according to this definition, what I have on this slide from this particular web page, is that a car which doesn't rely on any human for any subtask. So for example, you have a car which could park itself, but it cannot help you to drive it 24/7. That might again be a semi-autonomous vehicle. So this is the place where we are trying to go, where a car is smart enough that you can just punch some commands to it, and then you can just read a book, and you do not have to you have to be worried that maybe a camera may malfunction or a lidar may give so much load to the image processing algorithm that my car may collide. So you do not expect to be having a driver seat or driver controls on that car. That would be called a fully smart car.
Very well. Thank you, sir. We would now like to proceed with our event. I would like to call Mr. Muhammad Rafi Sheikh to present a token of appreciation for our esteemed speaker.
Thank you so much, host, for the opportunity. Just a second. Thank you so much, Dr. Samir Kazi, for your valuable presence in Student Activities Committee's webinar.
Okay, I thank you for the chance you gave me.
Thank you so much. Thank you so much. Also, I would like to appreciate. Just a second. Host, please, can you provide me a sharing access? Yep. I would also like to thank Ms. Navera and Ms. Sauda Anil, Chair IEEE PAF-KIET and Vice Chair IEEE PAF-KIET, also the team IEEE PAF-KIET Student Branch on behalf of Student Activities Committee, IEEE Karachi section, on this such a mannerful organized webinar. Thank you so much.
Thank you very much. It was totally our honor. We appreciate it a lot. On behalf of all the participants and our entire organizing body, we would like to thank you, Dr. Samir, for humbly joining us today and giving us your time. It was an honor for us. Thank you so much.
You are most welcome.
Thank you, Mr. Rafi Sheikh, for being with us here today. And we'd also like to thank our participants for joining us today and showing interest in our events. So thank you once again, everyone. Goodbye for now. Allah Hafiz.
Allah Hafiz.